The Heisenberg Uncertainty Principle has to be one of the coolest and also one of the most misunderstood and abused ideas in physics. So before I explain it to you, I want you to pick which of these three statements you think is the uncertainty principle. Now, this isn't to embarrass you, it's because it really helps to know where your preconceived understanding is flawed to be able to fix it. So please do it, it's for your own good. And even if you don't know the principle or none of these seem perfect, just pick the one that sounds most right to you, and in the corner of the video you can find a poll where you can enter your guess. Please pause the video now to read all of these and decide. Alright, I hope you've made your choice. Maybe you'll be surprised, but both 1 and 2 are very wrong. They demonstrate quite fundamental misconceptions about quantum mechanics. But what's worse, they make the Heisenberg Uncertainty Principle sound like it's about measuring. Here's the thing, it's not about measurement. The principle works whether or not you ever measure the particle. But before I explain that, let me try and convince you that the other two options really are just not right. Option 1 first. The really big issue with this option is that it says quantum particles really have a position and a momentum, just like classical physics, but they're just shy about it. This is not at all what quantum mechanics says. What quantum mechanics says is a particle doesn't have just one place or one speed it's going at. Instead, while they're not observed, they can be in what we call a superposition of many places and many speeds. But say you do go to measure it. You can only measure one thing about the particle, so let's say you're measuring the position. You're not going to see it in all of these places. It will just be in one. And it will pick which one randomly. And so that's one reason the first answer is wrong. When you measure a particle, it doesn't tell you some range of places or any other information about where it is. It just turns up in one single place. And what's worse is, you can't measure it again and hope to see all these other spots. Now it's not in a superposition of different positions anymore. If you measure it again, it will certainly be in this place. In the language of quantum mechanics, a measurement collapses the state, so the particle is no longer doing what it was before. So it's pretty meaningless now to measure the speed and try and deduce anything about the particle's speed before you measured anything. No, you've ruined the original state. I mean, you can measure the speed, just like with the position, and it will tell you just one speed, but that is in no way the speed the particle was really going at, or even related to the superposition of speeds the particle was in originally. So, in summary, the particle didn't have just one speed or position, but let's say you measure it, say its position, it would only tell you one of the places, and which one is random. Plus, you can't ask it again to get more information because it's no longer in a superposition of places. And worse, you can't ask the particle about its momentum now. The value you get is completely unrelated to the original superpositions of momentum. On the other hand, this option says that the particle really has one speed and one position, and that you can get some range of information about the particle's position, and that you can then go and ask about the momentum as well. What about the second option? This has got to be one of the most popular explanations of the uncertainty principle, and it's just so confusing because it's completely unrelated to the uncertainty principle. The principle is not about some very specific setup for measuring position. Implying that it is leads people to ask the very sensible question, well, why don't I just come up with a better way to do it? The Heisenberg Uncertainty Principle is not about measurement at all. I'll explain in a sec, but first let's address the issues of this one. It has some pretty similar misconceptions, that the particle really has one position and one momentum, and we're trying to outwit it to find them both out. It also seems to say that the uncertainty is from knocking the particle or in some other way disturbing the particle via measurement. Like I said before, the uncertainty has nothing to do with measurement. It's actually about the range of different speeds in the superposition. This range is the uncertainty referred to by the principle. But uncertainty is a sort of unfortunate term for it. Uncertainty makes people think that there is a speed, but we're uncertain about what it is. But no, quantum mechanics is so much weirder and more exciting than that. I mean, this second option is basically classical. There's pretty much nothing there that you wouldn't expect from real life. Quantum mechanics is not what you'd expect from real life. So let me explain the real Heisenberg Uncertainty Principle. As I was saying before, the particle is in a superposition of many places, but it's not usually equally in all of those places. Some places are weighted more heavily, which means that if you were to measure it, it's more likely to turn up in one of those places. But we're not going to measure it, okay? There's no measurement in this entire thing, just to make that clear. Now, let's say a particle is most likely to turn up in certain areas. There's a way to mathematically describe the total size of these likely areas. We'll use the symbol delta x. So a particle could have a really small delta x, which means that it's mostly in a superposition over a very small area, which again means that if we were to measure where it is, then we could make a pretty good guess about where the particle will turn up. This is probably why the term uncertainty is used to describe delta x, because it means how much we're uncertain about what result we would have if we were to measure it. I just don't like that word because of the connotation that the particle really is in one place, but we didn't have enough knowledge to know where. No, even with all the knowledge that quantum mechanics says is possible for anyone, there is still this randomness when you measure. Okay, so we can similarly talk about momentum. The particle is in a superposition of speeds. So which speeds are weighted the most heavily? Again, you'll find it's some range, and you quantify the size of this range mathematically in exactly the same way, and call it delta p. Now we have the stage set for understanding that famous misused equation. What it says is, in quantum mechanics, delta x and delta p can't both be as small as you want. See, if delta x was really small, but so was delta p, their product would be very small, and that's no good. It has to be bigger than this number. This is significant because while it's true that in quantum mechanics we know that the particle is in a superposition, we might have wanted to minimize how bad this is. We might have thought, well, at least if the particle won't just go at one speed, we could come up with a way to really narrow down the range of speeds in the superposition. And then, even if we had to accept that the particle is in a superposition of many places, at least we can make it mostly in one small area. Then this particle has almost one speed and almost one position at a time, and that means it's almost a classical particle. So it'd act almost the way we'd like it to. But the Heisenberg Uncertainty Principle destroys that possibility. There is no way to make a particle almost classical in position and almost classical in momentum. One or both have to give. The world is quantum, not classical, no matter what we wish.